Lie algebras, problem session 1, basics. Problem 1. Let G be the Lie algebra over the complex numbers with the bases e-1, e0, and e1, and the Lie bracket given by the following formula. The Lie bracket of ei and ej is equal to j minus I times ei plus j, where I and j are from -1, 0, and 1. Check that this algebra is well defined and that it is isomorphic to SL2. Solution. Let us first check that this algebra is well defined. To start with, let us check that the formula in the formulation of the problem makes sense. For this, note that if I is equal to j and is equal to 1, then the right-hand side of this formula is equal to 0 because of the factor j minus I. And so this right-hand side makes sense, despite of the fact that e1 plus 1, which is e2, does not exist. So the right-hand side in this case is interpreted as 0. Similarly, if I and j is equal to -1, the right-hand side is again 0 due to the factor j minus I, and so it makes sense despite of the fact that e minus 2 does not exist. So the formula in the formulation makes sense in this interpretation. Now let us check the Lie algebra axioms. We start with anticommutativity, which means that we need to check that the Lie bracket is anticommutative. So the bracket of x and y is equal to minus the bracket of y and x. Let us check it on the basis elements. The bracket of ei and ej is by definition j minus I times ei plus j. We can rewrite it as minus I minus j times ei plus j, which is by definition minus the bracket of ej and ei. So our bracket is indeed anticommutative on the basis elements. And then the general case follows from the bilinearity of the Lie bracket. Next, let us check the Jacobi identity, that the bracket of x with the bracket of y and z, plus the bracket of y with the bracket of z and x, plus the bracket of z with the bracket of x and y is equal to 0 for all elements x, y, and z of our Lie algebra. Again, due to the bilinearity of the Lie bracket, it is enough to check this on the basis elements. So if we plug in the basis elements ei, ej, and ek, then the bracket of ei with the bracket of ej and ek can be computed as follows. We first compute the inner bracket of ej and ek, and we get k minus j times the bracket of ei with ej plus k. This is equal to k minus j times j plus k minus I times ei plus j plus k. And so our sum in the Jacobi identity for the three cyclic permutations of ei, ej, and ek will be equal to ei plus j plus k with the following coefficient: k minus j times j plus k minus I plus I minus k times k plus I minus j plus j minus I times I plus j minus k. Now we can perform all multiplications, open all brackets, and we get the expression kj plus k squared minus ki minus j squared minus jk plus ij plus ik plus I squared minus ij minus k squared minus ki plus kj plus ij plus j squared minus jk minus I squared minus ij plus ik. And this expression is equal to 0. So here in this line we highlighted the things which cancel by the same color. So kj minus jk plus kj minus jk. these terms will cancel. Plus kk minus kk, plus ii minus ii, and so on. It's easy to see that in this line everything cancels. And this shows that the Lie bracket in our algebra satisfies the Jacobi identity and is anti-commutative, so indeed G is a well-defined Lie algebra. Let us now prove that G is isomorphic to SL2. Recall that SL2 has bases consisting of the elements F, H, and E, and the Lie bracket given by the following expressions. The bracket of H and E is 2E, the bracket of H and F is minus 2F, and the bracket of E and F is H. So now define the elements x minus 1, we set it to be the element E minus 1, we define the element x0 as 2E0, and we define the element x1 as minus E1. Of course, these are just scalar multiples of the original basis elements, so they obviously form a basis in G. Let us now check the Lie bracket for this basis. The bracket of x0 and x1 is the bracket of 2E0 with minus E1, which is minus 2 times the bracket of E0 and E1, and this is minus 2 times E1, which is equal to 2x1. The bracket between x0 and x minus 1 is the bracket between 2E0 and E minus 1. So this is 2 times the bracket between E0 and E minus 1, which is minus 2 times E minus 1, which is minus 2 times x minus 1. And finally, the bracket between x1 and x minus 1 is the bracket between minus E1 and E minus 1. This is minus the bracket between E1 and E minus 1, which is equal to 2E0, which is exactly x0. And now we see that the Lie bracket in the basis x minus 1, x0, and x1 looks exactly like the Lie bracket for the standard basis of SL2. And this means that sending E to x1, H to x0, and F to x minus 1 gives an isomorphism between SL2 and G. This completes the solution of problem 1. Problem 2. Let A be the Lie algebra over the complex numbers with the bases A, B, and C and the Lie bracket given by the following expressions. The bracket of A and B is C, the bracket of A and C is 0, and the bracket of B and C is 0. Classify all Lie sub-algebras of A. Solution. The original algebra A has dimension 3. So it can have only sub-algebras of dimension 0, 1, 2, and 3. Of course, the only zero-dimensional subalgebra is 0, and the only three-dimensional subalgebra is the algebra A itself. Next, since for any element V in A, the bracket of V with itself is 0 due to anti-commutativity, the linear span of any non-zero vector of A forms a one-dimensional Lie subalgebra. So two such subalgebras are equal if and only if the generating vectors differ by a non-zero scalar. So this classifies one-dimensional subalgebras in A. So we are left with classification of all subalgebras of A of dimension 2. Let B be a two-dimensional subalgebra of A. Assume first that the Lie bracket of B with itself is not 0. Then this Lie bracket is of course contained in the Lie bracket of A with itself, which coincides with the linear span of the element C. As the latter has dimension 1, and the Lie bracket of B and B is assumed to be non-zero, we get that the bracket of B and B is the linear span of C. In particular, the element C belongs to B. But C is central, so it commutes with the whole of B. And as any element of the Lie algebra commutes with itself, it follows that B must be commutative. So B has dimension 2, it contains C and something else. C is central, And so any linear combination of something else with the central element commutes with everything. So this contradicts our assumption that the Lie bracket of B with itself is non-zero. So this assumption is false, which means that the Lie bracket of B with itself is 0. So B is indeed a commutative subalgebra. Now we want to show that our element C belongs to B in any case. Assume that C doesn't belong to B, so B has dimension 2, C is outside B, so the direct sum of B with a linear span of C must be the whole of A. B is abelian, C is central. From this it follows that the Lie bracket on the whole of A must be 0, because any element in A is a sum of an element in B and some scalar multiple of C. But this is of course not the case. We know that the Lie bracket on A is not 0, so this gives us the desired contradiction, and so the element C is in B. Next, we know that for any non-zero element V, which is not a scalar multiple of C, the linear span of V and C is an abelian subalgebra of A of dimension 2. Indeed, C is central, and of course the bracket of V with itself is 0, so the linear span of V and C must be an abelian subalgebra of A, and if V doesn't belong to the linear span of C, this subalgebra has dimension 2. Of course, it is enough to consider elements V of the form alpha times A plus beta times B, because we can always remove the scalar multiple of C from this vector, where alpha and beta are complex numbers, such that the pair alpha beta is not equal to 0, 0. And of course, two vectors V of this form give the same subalgebra if and only if they differ by a non-zero scalar. This classifies all two-dimensional Lie subalgebras in our Lie algebra A and completes problem 2. Problem 3. Find a basis UVW of SL2 such that the Lie bracket between U and V is W, the Lie bracket between V and W is U, and the Lie bracket between W and U is V. Solution. Recall that SL2 has bases F, H, and E, in which the Lie bracket is given by the following expressions. The bracket of H and E is 2E, the bracket of H and F is minus 2F, and the bracket of E and F is H. Let P be the Lie algebra from the formulation. So it has the bases U, V, and W, and the Lie bracket given by the bracket of U and V is W, the bracket of V and W is U, and the bracket of W and U is V. It is easy to check that this defines the Lie algebra. So this operation is anti-commutative, and it satisfies the Jacobi identity. Now we are going to solve the opposite problem. We will find in this Lie algebra P a basis with the Lie bracket which is the same as the Lie bracket for the standard basis of SL2. The point is that this is easier to solve because the standard basis of SL2 has certain very nice properties which we can use. So in particular, if you look at the basis element H, then the adjoint operator of this element H is diagonalizable, it has simple spectrum, and the remaining elements of the basis are eigenvectors for this operator. And of course, the notions of diagonalizability, determination of spectrum, and the determination of eigenvalues is something which one can solve using the linear algebra. So let us look in our algebra P for some element which is similar to the element H in SL2. Let us take an arbitrary element in P, call it X, and write it as a linear combination of basis elements. So X is equal to alpha U plus beta V plus gamma W, where alpha, beta, and gamma are complex numbers. For this element, we can write the matrix of the adjoint operator acting on the algebra P. So this is a bracketing with X. So if we apply bracketing with X to U, then the first term cancels and we get the bracket of v and u times beta plus the bracket of w and u times gamma. And if we write the outcome as a linear combination of basis elements, we get the coefficient 0, gamma, and minus beta. That's the first column of our matrix. So the second column will be minus gamma 0 alpha, and the third column will be beta minus alpha 0. So that's a matrix. We need to find out whether it is diagonalizable. So we compute the characteristic polynomial, which means that we subtract x times the identity matrix and take the determinant. And the determinant will be minus x to the power 3 minus x times the coefficient alpha square plus beta square plus gamma square. So that's the characteristic polynomial. We want to find an element which has eigenvalues 0, 2, and minus 2. That's exactly the eigenvalues of H. So we are looking for an element like H in our algebra P. So the element with eigenvalues 0, 2, and minus 2 should have the characteristic polynomial x times x minus 2 times x plus 2 up to a non-zero scalar. So in order to get such eigenvalues, we can, for example, take beta and gamma to be 0, and we should take alpha to be 2 times the imaginary unit I. And note that if we would work over the real numbers, we couldn't do anything, since over the real numbers there do not exist alpha, beta, and gamma, for which this characteristic polynomial has eigenvalues 0, 2, and minus 2. It's very important that we work over the complex numbers and not over the real numbers. So if we choose such alpha, beta, and gamma, we get our H. So our H is 2 times the imaginary unit I times the element U. So for this element H, the adjoint operator has eigenvalues 0, 2, and minus 2. Of course, for 0, the element itself is the eigenvector. Let us determine the eigenvectors for 2 and minus 2. To determine the eigenvector for the eigenvalue 2, we take our matrix and subtract 2 on the main diagonal. Recall that alpha is 2i, beta and gamma are 0. So we get the matrix minus 2, 0, 0, 0 minus 2 minus 2i, 0, 2i minus 2. And the vector annihilated by this matrix is 0, 1, and then I. I is the imaginary unit. Which means that as the basis element E, that's the eigenvector for at H with eigenvalue 2, we can take the corresponding linear combination, which will be V plus the imaginary unit I times W. And now we will find the element F. The element F is the eigenvector for at H with eigenvalue minus 2. So we take our matrix, subtract minus 2 on the main diagonal, which means add 2, and find the vector which this matrix annihilate. For example, we can take the vector 0, 1 minus the imaginary unit. So the corresponding linear combination V minus the imaginary unit W will coincide with our element F, of course up to some scalar. And to determine the scalar, we need to use the Lie bracket equation that the bracket of E and F is equal to H. So let's compute this. Our E is V plus IW, our F is Xi times V minus IW. If we compute this Lie bracket, we will get minus Xi times 2IU. And this gives us Xi is equal to minus 1. And so our element F is minus V plus the imaginary unit times W. So we want now to have the base change in the opposite direction. We want to express U, V, and W via E, F, and H. This is very easy to do. Since H was 2 imaginary units times U, U is H divided by 2 imaginary units. Since our element E was V plus IW and our element F was minus V plus IW, we can express v as e minus f divided by 2, and finally w is e plus f divided by 2i. And this completes problem 3. Problem 4. Consider SL2 as a Lie subalgebra of SL3 embedded into the top left corner. So we have SL3, this is a Lie algebra of all traceless 3 times 3 matrices, and if you consider the traceless 2 times 2 matrices concentrated in this region, this will be a Lie subalgebra isomorphic to SL2. Determine the decomposition of the corresponding adjoint module, that is the adjoint action of SL2 on SL3, into a direct sum of simple SL2 modules. Solution. Recall that simple finite-dimensional SL2 modules are indexed by non-negative integers. For each non-negative integer n, we have the corresponding simple module L of n, which has dimension n plus 1. Moreover, the element h in SL2 acts on this module diagonalizably and with simple spectrum, which uniquely determines the module. In fact, the corresponding spectrum of H on Ln consists of the elements n, n minus 2, n minus 4, and all the way down to minus n. The algebra SL3 has dimension 8. If we consider the usual matrix units Eij, then we have the natural basis of SL3 given by the following elements: E12, E13, E23, E21, E31, E32, and then E11 minus E22, and E22 minus E33. The matrix of the adjoint action of our SL2 element H and our SL2 element H inside SL3 is given by the matrix 1, 0, 0, 0 minus 1, 0, 0, 0, 0. In our fixed basis of SL3 is given by the following diagonal matrix. So we have a diagonal matrix, which is 8 times 8 matrix, and on the diagonal we have 2, 1, minus 1, minus 2, minus 1, 1, 0, 0. So this means that E12 is an eigenvector for odd H with eigenvalue 2. E13 has eigenvalue 1, E23 eigenvalue minus 1, and so on. Great. This means that the spectrum of the adjoint action of H on SL3 is the following multiset. We have minus 2, then minus 1 twice, then 0 twice, then 1 twice, and then 2. The maximal element in this multiset is 2, which means that L2 is a direct sum. The spectrum of H on L2 is minus 2, 0, 2. If we remove it from our multiset, what is left is minus 1, minus 1, 0, 1, 1. The new maximal element here is 1, and it has multiplicity 2. This means that L of 1, direct sum with itself, is a direct sum. On this direct sum, H has the spectrum minus 1, minus 1, 1, 1. And if we remove the spectrum from what we have, what remains is just 0. And this is exactly the spectrum of H on L0. Consequently, as an SL2 module, SL3 is isomorphic to L2 plus L1 plus L1 plus L0. And we can even check that the dimensions agree, so we have 3 plus 2 plus 2 plus 1, that's equal to 8. This completes problem 4. Problem 5. Compute the following two expressions in the universal enveloping algebra of SL2 and write the outcome in the PBW basis f to the power I, h to the power j, e to the power k of this algebra. The two expressions are the following: the Lie bracket of h with f squared e cubed, and the Lie bracket of fh and he. Solution. Recall that the adjoint operator is a derivation, and so it obeys the Leibniz rule. If we apply the bracket with h to something, the outcome is equal to the sum of applying the bracketing with h to each individual factor in our monomial. So the bracket of h applied to f squared e cubed is equal to the bracket of h applied to f times f e cubed plus f, the bracket of h applied to f times e cubed, plus f squared, the bracket of h applied to e, times e squared, plus f squared e, the bracket of h and e times e, and finally plus f squared e squared, the bracket of h and e. The bracket of h and f is minus 2f, and the bracket of h and e is 2e. So we have the coefficients minus 2 from here, minus 2 from here, 2 from here, 2 from here, and 2 from here. Adding up all the coefficients, we get the total coefficient 2. So the answer is 2 times f squared e to the power 3. For the second expression, we just write down the definition. The bracket of fh and he is equal to fh squared e minus hef h. So the first element is already in our PBW basis, so we need to compute the second one. Minus hef h, we swap e and f. So this is equal to minus hfeh minus h cubed. H cubed is fine, so we compute minus hfeh. Minus hfeh, we swap h and f, is minus fheh plus 2 times feh. So here we swap e and h, so this is minus fh squared e plus 2fhe, and here we swap e and h, plus 2fhe minus 4fe. And now we take this, which cancels here, and now if we add up these 4 summands, we get that the answer is 4 times fhe minus 4 times fe minus h cubed. And this completes problem 5. Thank you very much, hope you enjoyed this problem session, and see you next time.